Hello, everyone, and welcome to today's webinar, The Future Cable Network Enabled by Packet Transport and Virtualization. I'm Joanne Emery, and I lead the webinar events team at Infonetics Research, part of IHS, and we want to thank you for sharing your time with us today. Our panel will be discussing how cable networks of the future will be built, the impact of technologies like SDN, NFV, DOCSIS, and also how cable operators and MSOs can make their service delivery more efficient and more effective. And our webinar today is co-presented by the Infonetics IHS team, our sponsor Juniper Networks, and their partner Gainspeed. So before we start your presentation, I want to mention some features on your console and also talk about how you can participate with us. First of all, your webinar console can be customized so you can move or resize any of the preloaded windows. You can maximize your slide view just by clicking the top right corner of that window, or you can drag the bottom right corner of any window to resize your view. In addition to those preloaded windows, you'll see a number of buttons along the bottom of the console, and these contain more features. One button I want to call out is the resource list. It's the button that looks like a little file folder. That's where you can find the copy of today's slide deck along with a companion report for the webinar. In addition to those items, we just have a lot of other great information on today's topic posted there. So you can download technical papers, access videos, and more. So check out those materials right on that resource link. And also, if you do experience any technical difficulty during the session, you can click on the Help widget. It's the icon with a question mark, and you can find answers to common technical issues right there. And now I want to talk about some ways you can participate today. First, you're going to see a Twitter feed on your console, so you can easily tweet right from the webinar. We will be using the hashtag CableIP today. Also, during the webinar, we have a poll question for you. We want your feedback, so watch for that and please participate. Lastly, directly after our presentation, the panel will be answering your questions. We want your input, so please enter your comments and questions anytime during the presentation. Just use the Q&A box that's located on the left side of your screen. We'll try to get to as many questions on the session as possible, so we'll get your questions in early. Any questions we can't get to on the call, we will follow up with you after the webinar. And now I want to just introduce the panel for the session today. First of all, leading the discussion is Jeff Hainan. Jeff is Research Director for the Broadband Access and Pay TV segment at Infonetics Research, IHS. Also from Juniper, we have Andrew Smith. And Andy is Distinguished Engineer and Chief Architect for Cable MSO Networks at Juniper Networks. And rounding out our panel today, we have Samir Parikh. And Samir is Director of Product Management at Gainspeed. And with those introductions, we want to get our presentation started. So I'm going to turn the controls right over to Jeff. Jeff, to you.
All right. Thanks, Joanne. And hello, everyone. Thanks for joining us today. Just a quick overview of today's agenda. First, I'm going to go over some market trends that we're seeing specifically here in for cable MSOs. Then I'm going to hand things over to Andy Smith of Juniper to talk about the business and technology evolution for cable operators. And he's going to go into some more details about metro packet transport. And then we're going to have our poll question in between. And then Samir Parikh from Gainspeed is going to talk a little bit about the virtualized CCAP. And he's going to hand things back to Andy to go over specifically Juniper's product lineup for cable operators. I'll come back and wrap things up, and then we'll open the floor to your questions. So, cable operators obviously are facing a number of challenges, just as all operators are, really from increased competition to fundamental changes in their service offerings, as well as the technology shifts that they use to deliver those services. In terms of competition, cable operators face increasing threats from telcos, municipalities, utilities, upstart ISPs that are pushing more fiber to the home throughout their networks. Obviously, in addition, OTT service providers, anyone from Netflix to Hulu to Vonage, Apple, Amazon, you name it, also threaten the top-line revenue growth. And finally, though cable operators have been very successful in growing their enterprise customer base, telcos are really fighting back right now with aggressive pricing and a larger reach of fiber-based services. Those changes in the competitive landscape have meant changes in the service focus for cable operators as well. As we know from the numbers, pay TV and broadcast TV is no longer the lead service it used to be. And instead, growth is coming from residential and enterprise IP and data services, as well as Wi-Fi connectivity and mobility, and finally also retail and hosted cloud services. And those specific service changes are resulting in technology shifts in their networks. And that means more rapid upgrades in those technologies that cable operators employ. In a lot of cases for operators, the DOCSIS 3.0 transition isn't even over yet, and we're already talking about DOCSIS 3.1 beginning later this year. And also, as Comcast and Bright House and other operators have shown, fiber to the home, fiber to the business is also becoming a larger part of the access network. And then most importantly for these cable operators, end-to-end IP is really becoming the norm. And so some of those technology shifts that I track in my quarterly reports, we can see here directly in the access network specifically, cable operators have been adapting to some of these competitive and technology changes by increasing the throughput and capacity they have in their DOCSIS access networks. So you can see that from 2013 to 2014, the deployment of DOCSIS downstream channels effectively doubled. And obviously we expect that DOCSIS 3.1 is only going to push channel deployments even higher over the coming years. And then following along in edge and core networks, the long-term transition to IP and all-packet networks continues, driven largely, as we note here, by the tremendous growth that we continue to see in unicast and over-the-top video, as well as mobility, including those Wi-Fi services I mentioned earlier. And of course, though cable operators are a small part of the equipment revenue that we see here, the same high-level market dynamics that are driving the overall increased purchases of IP edge and IP core routers are also driving those same purchases for cable operators globally. And obviously, like their telco competitors, those purchases, whether it's in the access network or in the edge and core, those purchases are being made to facilitate that transition to all-packet networks. Really because, like telcos, their cable operators have similar network issues to overcome. We note here that cable operators do have a challenging mix of IP, TDM, analog, and optics and optical technologies across their access, edge, and core networks. In addition, with their heritage in broadcast TV, most cable operators still use statically provisioned QAM channels and wavelengths that really can't be adjusted based on the type of rapid traffic and service flow changes that they continue to see increasing in their networks today and tomorrow. And obviously, those legacy technologies all bring with them different and fragmented OSS systems, which lengthen provisioning times and make it difficult and challenging at times to turn up new services for subscribers. And finally, I think one of the biggest concerns for cable operators is that new services simply require too many expensive truck rolls, whether that is to enterprise or residential subscribers. So clearly that needs to change in order for them to remain competitive. So with that, I want to hand things over now to Andy Smith of Juniper, who's going to provide us some answers on how to address those challenges. Andy?
Thanks, Jeff. It's a real privilege to participate in the webinar, and hello to everyone out there in webinar land. We're going to talk a little bit about cable networks today, and specifically how cable networks are evolving and how the service trends that cable wants to deliver are changing, and technology we can apply to deliver those new services. So as Jeff said, a lot of what cable is delivering is moving towards packet services. And of all these different services, this is just a small subset of new cable services that are emerging. It's really all about video. Video is the dominant consumer of bit traffic on cable networks today. It's moving towards a unicast environment, an adaptive environment, And video used to be, not that long ago, a kind of very brittle, fragile service to deliver over a packet network. Now it's a very robust, and you could almost argue abusive service of modern packet networks. So we see that video becoming the real driver of not only traffic on these networks, but also new and quite innovative revenue models for cable operators to explore. There's also this notion of using cable technology to deliver VPN access, using cable technology to deliver commercial services, and certainly this whole notion of delivering gigabit or gigabit plus residential internet has certainly taken the industry by storm. At the same time, there's a number of new technologies that are emerging on the market today. And one of the ones that Samir will speak to later is this notion of a full spectrum last mile, or this ability to get to an all IP last mile. For a long time, DOCSIS itself was just considered perhaps a channel in the lineup. You'd have CNN, HBO, and then DOCSIS. But what we're moving towards fairly quickly is DOCSIS becoming the entire lineup, all services to the home being delivered over IP. And what we're going to speak to today is if that's our trajectory and if that's how we want the network to evolve, then it makes better sense to build the entire network upon packet technology instead of what we have today, which is for the most part a diverse or a network that has multiple layers. If everything is going to be delivered over packet, then the fundamental building block of the network should be the packet. When we talk at Juniper, when we talk with our major customers, including cable, and cable networks are unique in that they have tens of millions of subscribers, all with very dynamic flows. The traffic is, while it's predictable, it's also unpredictable at the same time. But all big internet operators ask us kind of the same thing. The first thing they ask us is, help us reduce our operating costs. These networks are too complex. These networks have been built up over time. The guy that put it in has since left. There's layers of scar tissue in the network. But help us reduce the operating cost of these networks. And we hear that over and over. The second thing that major customers ask us is, help us to become more agile. We need to move faster. We need to be able to deploy services faster, recognize revenue from those services faster, and even be able to turn them down faster. So the business has evolved to a point where the network cannot and does not need to stand in the way of the business. And then finally, the last one is actually help us reduce CapEx. So that's not the first one. It's actually the last one that people say, which says to us that the industry is willing to invest to reach these goals. And it also shows that the industry for equipment vendors is quite robust as well. There are 4 startups now in Silicon Valley just focused on packet forwarding silicon. So there is quite a bit of investment that is willing and able to reach these goals to build a much more agile and operationally efficient network. And then among cable and the large service providers, it's help us monetize these networks. How do we make more money? What can we do with these networks that actually produce more in the way of revenue? Networks are unique in that data in motion, or data traveling across a network, intrinsically has more value than data at rest. And so the more bits that you can put in motion and the more value you can add to those bits while they're in the network, all goes towards helping to monetize the network for large customers and large operators. But if we drill down a little bit on cable, the fundamental challenge that they're facing is this overwhelming demand for unicast video. When cable networks first went to a converged model or a triple play model, around 10 years ago, and when CMAP or then CCAP was later proposed, the growth in video on demand consumption was about the same as the growth of internet consumption when you looked at it from the bit transport level. Well, what's happened within the last 5 or 6 years, as we all know, is that video, or specifically the software that delivers video over the top, has advanced in such a way that it's a dramatic change in how the network is used. Video is no longer kind of a static, predictable amount of bandwidth. It's now very variable. And we're creating an environment where if we don't change how we build and operate these networks, we think that we're going to end up with a considerable capacity gap in the not too distant future in cable. And if this isn't addressed by looking at the network fundamentally different, the problems could manifest itself in cost or constraint or in other business imperatives. And we just don't want the network to get in the way of not only growth and quality of experience for consumers, but for the business models of the operators themselves. So we think that to get to this world, we really need to make the building block of the network the packet itself. And if we think about networks themselves or packet-based networks themselves, there's really only been two major advances in the past 40-some years in internet and packet-based networks. The first being the concept of statistical multiplexing or packet switching. This is a base principle, first popularized by a guy named Len Kleinrock about 40 years ago, wrote his PhD thesis on packet switching, and it is one of the fundamental technologies that the internet and packet networks is still based upon. And the second major advance in networking was the notion of dynamism or of topology discovery. We kind of take both of these for granted these days. We can attach a router from any vendor to another router from any vendor, turn on a routing protocol, and it starts working. But these are still the base principles upon which we build networks today, and that's not going to change. What's happening now, though, is we're applying software and automation in ways that we haven't in the past. I'm kind of an old school router guy. I cut my teeth on CLI and went through all the vendor certs and such. But we're not going to build networks like that at the scale we have in the past anymore. We're going to use software much more extensively. We're going to use software to stitch together parts of the network that previously had nothing to do with each other. We're going to use software to turn up and turn down services. We're going to use software to build something new. This isn't just simply turning up and down ports. That's been done for years. But rather, we want to use software and specifically automation to create a network that is better than the sum of its parts. And we'll talk about how we think we're going to do that. At the same time, to do this, to get to a network that is malleable and automated, we need to get rid of this notion of building networks in discrete and fixed units. And what's a fixed unit? Well, it's a part of the network that requires manual tracking, allocation, sorting. So like optical waves, VLAN tags, the whole notion of assigning downstream spectrum to a specific service needs to go away. And like I mentioned before, manual CLI also needs to go away. We have the technology now to fix all of this, to eliminate all of these fixed units and then some that aren't even listed here. And we want to apply them for maximal benefit in cable. If you think about how technology has evolved and why we want to eliminate this notion of fixed units, you just need to look at the lesson from the Industrial Revolution. And that is that when you invest in technology or when you invest in automation, over time, the cost to do any unit of work will decline. If you're on the inflation curve or the curve that requires lots of effort, and that effort could be physical effort, it could be mental effort, it could be both, over time, your cost is just going to increase exponentially. There is some sort of a factor at work there. It could be, you could argue what that exact factor is, but regardless, over time, if you don't have systems that are automated, it becomes more expensive. And in the 60s and 70s, we saw this. You no longer have massive buildings full of file cabinets. All of that's automated. You no longer get paper airplane tickets. That's all automated. Just think of the things that automation has really brought to make more efficient to us. We haven't quite applied automation principles to networks yet, and that's one of the major initiatives that we're advocating for in today's webinar. So if we look specifically at cable architectures, there's two main areas of the network that we'd like to focus on today. The first is the optical transport system that's in the metro or the regional networks. And the second is the analog transport that's present in the access layer of the network. In both of these parts of the networks, we've effectively concentrated packet switching. Right, so in the metro side, we concentrate packet switching at an aggregation router, which then requires us to build aggregation routers that are either oversized or too big or too dense, and that's not necessarily required to have an aggregation router of that size to deliver the amount of bandwidth being consumed. But rather, that aggregation router being so big is simply an artifact of the transport layer not adapting packet switching and routing. And on the access side, this notion of CMTS as a centralized chassis is really a vestige of when DOCSIS was just a channel in the lineup. It made sense when the take rate was low and this whole high-speed data thing might have been uncertain to have a chassis-based CMTS that you could then take a certain amount of DOCSIS capacity and distribute it widely from the hub. That whole notion is now obsolete. And we think that as the world moves towards an all-packet environment, it makes much more sense to not only retire the analog transport, push Ethernet deeper, but distribute the functionality of the CMTS deep into the network. And this is how we've built internet networks forever. The more you can distribute packet switching into a network, the more robust system you build, the more scalable system you have. And we think that if you add software and automation into that mix, you build a better network for the long run. So let's talk about some specific technology examples for today's discussion. We're going to talk about this notion of using packet for transport in the metro. What does this really look like? What is the benefit of it? We want to get to a point where we have effectively a Shannon's limit interface on the router. I attach a piece of glass, or bandwidth, an increment of glass. I attach a piece of fiber to the router. I light up 8 terabits, and off you go. And we're going to talk, Samir is going to speak a bit about virtualized CCAP, how we can modernize DOCSIS, adapt it for the new world that we're speaking of here. And across all of these, this notion of software and automation applies extensively to make all of this work together. Before I move on, I'm going to toss it back to Jeff.
Okay, thanks, Andy. And before we jump back and I hand things back to you, I want to just remind the audience that go ahead and address your questions or submit your questions now. I suspect that we're going to get quite a bit more as we get here into the details of the product and network architectures. But go ahead and get them in early so that we have a chance to organize them and make sure that they're addressed. So with that, back to Andy.
Great. So let's talk a little bit about transport. And when we talk about transport, we're talking about it specifically in the metro. And the reason why we think the metro is one that's important to focus on is it's the area of the network that is going to see the most growth in cable. We see across all of our major cable customers more and more localized peering for content, more and more co-location of content in the metro or the regional network. And so if there's any place that needs to benefit from this notion of packet switching efficiency at the transport layer, it's in the regional and metro networks. And one of the reasons why I want to go about this is, as router people, I'm a router person. As I mentioned earlier, I'm used to being able to attach 2 routers together. It can be from 2 different vendors, and having a service come up and work. Well, we can't do that in the optical world, and there's no good reason why not. Right? I want to be able to deploy a transport layer with the same ease and effort that I do a router. I want to be able to have vendors that can mix. I want to get away from this notion of it being a black art, of there being an optical guy that has a power meter. All of that can and will go away. We can automate all of that and create an environment where transport, routing, and the packet layer are all the same. And cable is actually quite ripe for this because in cable, as it says here, the vast, vast majority of traffic is already IP over Ethernet. It's the exception to the rule. In fact, it's the kind of rare exception to the rule where there is an actual requirement for an optical wave for a service. And even those services that require optical wave, you could argue, could be moved to packet fairly reasonably. But it's this disconnect between the packet guy and the transport guy that creates a lot of inefficiencies in cable. We have a guy that owns the glass in the ground, a guy that owns the wavelength on the glass, a guy that owns the packet on the wavelength, and someone else that owns the application in the packet. All of that can be reconciled and made more efficient through some new modern techniques. And packet switching is really the key to all of this. And why is that? Well, we know that packet switching gives me an any-to-any network. Right? I can put a packet into the network anywhere, and it will find its way to the destination. That was one of the very, very key insights of IP versus in the olden days versus ATM or other then competing technologies is that IP is connectionless, and it is an any-to-any transport fabric. At the same time, we can build transport routers now that are very, very efficient and have low latency. So it's no longer the case that I need to worry about the transit time of a packet through a router. Just as today, I don't need to worry about the transit time of a photon through a ROADM. We can now match that, if not even exceed it slightly. We also need to be able to apply policy to packet networks, and MPLS-TE and other emerging alternatives to it are one way to apply policy to networks. Most traffic that's present on cable networks today doesn't need any sort of explicit policy to deliver a service, but we may need to apply some policy in networks to either help routers depreciate in networks longer. There may be business objectives to applying policy on packets, and there are many ways to apply policy. MPLS-TE is one of them, and it shows that we can build a router with a very optimized data plane for transport that does not require sacrificing the control plane. And finally, we need to make these systems programmable. One of the things that we really emphasize here at Juniper is the programmability nature of our silicon and software. But in this case, in fact, in all cases, we're going to make these programmable based upon open standards that any vendor can implement, specifically PCEP and some related protocols that we'll talk about in a coming slide. We're building routers now that are innovating in different ways than we used to. It used to be that we would build a router by basically constructing a barn-sized chassis and filling it full of jet fans and silicon that could do every feature you ever wanted. And we're not doing that anymore for core. We're now building routers that are smaller, that fit under a desk, that plug into an AC outlet, and can still switch tens and soon hundreds of terabits of traffic. We do this by innovating by throwing features away. Right? So by focusing on what a core router should do, we're able to now address a problem that we really couldn't before, which is the transport layer. If I'm going to come to a customer and legitimately say that I think a router can replace a ROADM, then I need to have a router that's lightweight, power efficient, low latency, and has the same physical footprint as a ROADM or a similar device. And we've built that. So what we have now is a trajectory of building routers that are extremely power efficient, thermally efficient, but can switch hundreds of terabits per second with optics that are integrated in them. And this lets me build effectively an infinite degree ROADM with policy and with an efficient transport system in a network. At Juniper, we have this box called the PTX 3000. It's that little thing in the top right there. It's just that. It's intended to be a router that is very small. It's about the depth of an iPad, but yet it has the same forwarding capacity as one of our competitors' very large, oversized routers. And we do that by investing in innovating in silicon. When we talk about packets, so why packets for transport? The key to making this part of the network work with packet switching is the notion of statistical multiplexing. In a network today, when we allocate transport paths, we really allocate circuits. And these circuits could be waves. They could be OTN circuits. And we also have the same phenomena present in the last mile by allocating downstream spectrum to services. But effectively, what happens is you have multiple flows of traffic on the network today, but they all don't peak at the same time. Right? So the more flows, more unique flows you have in a network, the more you can take advantage of the benefits of StatMux. And what we see is that at the transport layer today, we are effectively not taking advantage of this phenomena. We allocate a certain amount of bandwidth or spectrum on point-to-point interfaces, and those interfaces can peak at the same or different or multiple times, yet no matter what, I have to provision enough transport bandwidth to accommodate that peak. And this manifests itself then in building a transport network that's too big and an aggregation router that is oversized. The exact same phenomena, as I mentioned, happens the same way on the last mile on the analog laser today, because the lack of StatMux, the lack of packet switching, requires that I allocate spectrum for DOCSIS that may not be used all the time or at peak, or peaks are at different time for different flows. So we end up with this inherent inefficiency in the network. We did a study with a major cable operator to see, well, given that all of the vast majority anyway of traffic today is unicast video, is there still a benefit of StatMux? And what we did was we collected what are called LSP stats, or basically logical path MPLS stats, in the core, and we found that when you crunch the numbers, you get what's called a variance. And by having a result greater than 0.8, it shows us that of the individual flows on the network, there are peaks happening at many, many different times over time. And so we see that there is, yes, of course, a benefit of having routing in this operator's core. So for example, if they were to tear all the routers out and replace the core with point-to-point optical links and not do any routing in the core, there would be much, much more capacity required to be deployed not only in the core, but all around the perimeter of it to deliver the same amount of data. So StatMux brings us efficiency. The traffic that we're running on networks today benefits from StatMux, and we think that we can apply that same approach to the rest of the network. How does this look specifically? Well, if we have a router that's small and lightweight and able to fit where a ROADM fits today, or be an accessory to a ROADM, then we can integrate the transponder onto the router. We can perhaps integrate in the future a Shannon's interface, and we can integrate management of the inline amps. Because this is all packet-based, we can use what's called a path computation engine, which is an open standard. PSEP is an open standard, to then understand what's happening on this network and perform analytics. We can feed analytics and feedback from the application layer into this appliance. We can analyze exactly what's happening in the network in real time, and then install logical topologies on the network in the form of LSPs managed with RSCPTE in real time. And today, to change the transport layer of a typical network can be days, weeks, months. We want to do it in seconds. So effectively what we want to do in the big picture for future cable networks is to move the division between Ethernet and IP, today which is in the hub, all the way down to the outside node. And by doing that, every place from the regional aggregation to the edge router to the hub to the node is built on standard Ethernet, standard packet switching, able to benefit end-to-end from a packet transport architecture. These networks will be automated. These networks will be optimized with software and will take advantage of the very nature that the internet was built on, which is packet switching, to the maximal benefit. And with that, I will pass it back to Jeff.
Okay, thanks, Andy. So as I mentioned earlier, we had a poll question, and I want to put that out there now. The question is, what is for the cable operators in the audience? What is your timeline for deploying DOCSIS 3.1? So go ahead. Obviously, timeline is there: 0 to 6 months, 6 to 12 months, 12 to 18 months, beyond that, and then no plans. So go ahead and submit your answers now. And then while we wait for just a couple of seconds for the answers to compile, I'll mention again to go ahead and submit your questions now so that we can get them in and get them organized. We've got a number of them in there now, but please go ahead and add some more now. All right. So interesting results. Samir, I'm gonna hand things over to you, Samir Parikh from Gainspeed, to address the results here, and then also to go ahead and start your part of the presentation. So, Samir.
Thanks, Jeff. Definitely interesting poll results here. A large number of folks are saying they don't have plans for 3.1 at this time. I think it makes sense. It's just based on where the maturity of the technology is. I think if we ask this question 3 or 6 months from now, we'll get a very different answer. But very, very interesting. All right, so let's launch into the next section. So what I want to talk about is, Andy alluded to how we can leverage, packet switching in the cable network, and a big part of that is how do we evolve that access network. And to do that, at Gainspeed, partnering with Juniper, we're building a virtual IC cap solution. So let's talk a little bit about what that is. But before we kind of get into that, one of the big things that we see today, and Andy alluded to on the access side, is bandwidth is very incremental in terms of 6 megahertz channels, you have a certain amount of DOCSIS capacity. But when people look at bandwidth to the home, the coax really isn't the problem. There's a lot of conversations around, should we go fiber to the home? What's the evolution of the last mile? But that coax connection going in everybody's house is fundamentally capable of doing 10 gigs. It's really kind of encumbered by the way it's been used today, right? And what creates the limitations are a number of things that are part of the traditional HFC architecture. Your legacy, the optical transport, which is kind of expensive to maintain, proprietary, very cable specific. The notion of the centralized CMTS or CCAP chassis that takes up a lot of power and space and has a limited capacity. When you start coupling those two with the analog transport, you have challenges on RF signal quality so that it's harder to get to those higher order modulations with things like DOCSIS 3.1, like the poll question just talked about. And so, if you want to get to 10 gigs on a coax, you want to start getting to 4K QAM with DOCSIS 3.1, you need a different sort of physical architecture of the network. And then, if you look at the notion with DOCSIS 3.1 about how we're trying to get rid of these fixed spectrum divisions of 6 or 8 megahertz channels and go into more flexible channel bandwidth that can be anywhere from 24 megahertz to 192, that also gives you additional capability, ability to add capacity to the network and then have consumers take advantage of it rather than, everybody going from a 4-channel cable modem to an 8-channel to a 16. So we definitely have a number of challenges in the architecture that with the virtualized CCAP architecture in DOCSIS 3.1 we can address. So what is a virtual CCAP, right? So when you think of it, fundamentally it's a CCAP. So from a function standpoint, from the way it operates in the network, it is a CCAP. It has the same back office interfaces. It works exactly the same way when it comes to service provisioning for all of your services, whether it's video, whether it's data, whether it's voice. It's just been more intelligently partitioned, so we take those functions and take advantage of the advances in software-defined networking and, the modern silicon that, Andy talked about are in the Juniper routing platforms to distribute a number of these functions. And so, one of the hallmarks of the virtual CCAP architecture is this notion of a full spectrum DOCSIS element that is our Ethernet node that gets pushed out into the outside plant. And that replaces a traditional fiber node. And what that gets us is the ability, day one, today, to go to 6 gigabits on a single coax with full spectrum DOCSIS 3.0 and scaling that to 8 and 10 gigabits with a combination of DOCSIS 3.0 and DOCSIS 3.1. So it's a very unique capability, the industry's first and only product that does full spectrum DOCSIS today. And by pushing DOCSIS and all the RF pieces out into that Ethernet node in the outside plant, we now take advantage of Ethernet technology for transport that, again, we're going back to Andy's theme of packet-based switching, right? So I have 10 gig Ethernet that I now take from my outside plant to the routing layer in the hub, and then obviously that continues on into the rest of the network. So you get away from legacy analog transport that's based on 6 or 8 megahertz channels, and now you get Ethernet and packet switching out of the outside plant into an intelligent IP layer. And then we tie this all together with our sort of virtual CCAP controller, which is, think of it as a mini SDN controller, very focused on sort of a CCAP application that automates, discovers, and manages this entire ecosystem of products to create that CCAP experience and CCAP interface. So it's the power of software that allows us to take these different elements and entities and pull it all together as one single unified CCAP from an operational standpoint. Now, when we look at use cases for this, we see a lot of different use cases. We talk to a lot of operators today, and the most common thing that comes up in terms of where is the most immediate benefit is around going after multi-dwelling units or MDUs. One of the biggest challenges in MDUs is as you get into these apartment complexes, I've got 50, 100, 200, 500 users there. Well, you kind of need to dedicate capacity to them, but how do you provide that in the legacy environment? Doing dedicated nodes to an MDU becomes a very expensive proposition from a CapEx standpoint, from an OpEx standpoint, because of the power and space on the head end. And so it creates a number of challenges. Now, if we were to extend the virtual CCAP architecture for an MDU, you could put that Ethernet node in the basement, still use the coax in the building, provide all the services, whether it's existing QAM video, existing analog video, DOCSIS-based services, all of that you can kind of flexibly allocate, but then still leverage 10 gig Ethernet back into the hub and head end and kind of create this packet infrastructure. And now, for an operator, you have a 10 gig Ethernet connection to the MDU. It's not a fiber to the building play, so it kind of changes the marketing message. The cost structure of a virtual CCAP architecture relative to a legacy CCAP architecture dramatically different, so that makes it easier for them to go after and bid after these multi-year contracts. And then it's very easy to turn up MDUs in this way, because your MDU, every MDU, put a node in the basement, a 10 gig link, leverage that metro sort of optical core that you have for Ethernet services, and just sort of add, node splits by Ethernet, right? So we call it Ethernet-based node splits, where you're not adding a lot of equipment in the hub. There's not a lot of RF cabling or management in the head end or hub. It just, you get a 10 gig connection, pop a node, and that lets you kind of drive that. And again, all of this is automated through our virtual CCAP controller from a configuration and management standpoint. Now, obviously the big rage is, so I have this platform in there, but how do I scale services? Well, when we talk about getting to, over-the-top video and changing the video experience, one of the big fundamental challenges there is, how do I get to a gigabit service tier, right? This is one of the questions we get a lot of times, is like, how do I compete with fiber to the home in an HFC architecture? Well, today, you have the capability to do it. If you had a gigahertz plant, which you can get to in an MDU environment again, you can allocate 32 plus channels for DOCSIS 3.0. Like if you did 48 channels of DOCSIS 3.0, you have a gigabit and a half to that service group. That's with existing technology today. You layer in DOCSIS 3.1, where you have downstream capabilities by the end of the year. You can add another 2 gigs of capacity by allocating some spectrum there. So as you make that shift from legacy video services to IPTV, now you can free up some spectrum to enable that. And then lastly, you can start getting to symmetric services, which is sort of the last bastion of the claim to fame for fiber to the home, by moving the upstream split from 85 to 200, and then again leveraging DOCSIS 3.1. So the technology building blocks are all there. So we have the capabilities today to do what we call a gigabit HFC, all enabled with software, because each and every one of these transitions is software driven and software enabled. There is no discrete new piece of hardware that you need to put out there. There's no discrete piece of silicon that we need to build for it. It's leveraging software to enable these sort of transitions as you transition your service mix. So a lot of flexibility, very easy for you to do that. One of the other things that we talk about in the context of DOCSIS 3.1 is the notion of RF performance. So one of the things that we've done that's pretty unique in the Gainspeed architecture is leveraging the concept of a software-defined radio. That gives us the ability to do full spectrum DOCSIS 3.0 today, to move that to DOCSIS 3.1, to let you, through software, change between QAM video and DOCSIS on the fly. But it also gives us the ability to provide a much better RF signal onto the coax, and therefore provide a much better quality of experience to your end customers. Because we do that direct digital synthesis in the node, everything is digital until we get to that Ethernet node, and then we get to that first analog link. You see a much improved signal to the home. So when you talk about getting that end-of-line SNR for 4K QAM for DOCSIS 3.1, we see that being as a very easy proposition in this architecture, while we see it as impossible in this kind of legacy centralized architecture with analog transport in it, centralized CMTS or CCAP. The other sort of benefit you get, again, by the power of software and distribution and leveraging different fundamental building blocks is the whole notion of power and space. It's like, there's this big initiative at SCTE for Energy 2020, but how do you reduce your overall power consumption? That's a big piece. We're a big piece of that puzzle. When you look at deploying 100 MDUs or 400 service groups, in a very traditional CCAP architecture, you're looking at 8 chassis, 6 racks, and that's kind of the best of breed. I mean, you can't actually buy CCAP chassis that have that capability today. You need another generation or two of line cards for that to happen. Versus in a virtual CCAP architecture, because we've distributed so much of the processing into the outside plant, centralized a lot of the control and management through software, and taken advantage of kind of the modern routing and silicon in the Juniper platform, we sort of get this big sort of power and space reduction. So we can do that same equivalent deployment in half a rack. So you're talking $200,000, $250,000 worth of power saving, cost for power savings every year, 12x reduction in rack space. So very different sort of economics from an operational standpoint when you start looking at taking advantage of software-defined networking and network function virtualization in the context of our virtual CCAP architecture. So when you look at an overall TCO, we've done a number of models together with different providers. You'll see that from a cost standpoint, the virtual CCAP architecture saves you on a number of fronts, right? On the capital side, it's less than half the cost of a traditional CCAP architecture, a legacy CCAP architecture. It's about a third of the overall OpEx. Large part of that OpEx savings comes from power and rack space, so real estate. But the other sort of untold benefit is this notion of fiber efficiency. When you have an analog transport infrastructure, you have 4, 8, maybe 16 wavelengths on a fiber, versus when you start looking at going to Ethernet transport, you have today 80 wavelengths of 10 gig that will migrate to 80 wavelengths of 100 gig. So when Andy was talking about, bandwidth in increments of glass, you start looking at the amount of capacity you can provide in your fiber infrastructure by making every fiber be digital and have 10 gig Ethernet or increments thereof on it rather than legacy analog transport. There's a huge sort of cost savings there. There's a huge opportunity to monetize that fiber asset in a different way. So when we look at the value proposition, kind of just to close, we think there's think of it as 4 high-level quadrants, right? One is around real estate, and how do we help operators reduce their real estate footprint, the ability to potentially get rid of some hubs and head ends and consolidate it to optimize that, lower your ongoing operating costs in terms of power and space, cooling, truck rolls in terms of how do you have, with the RF performance in the plant, the ability to automate everything through software. How do we make it easier to manage the network? There's an increased revenue opportunity when you start thinking about doing multi-gigabit services over coax. You can start hitting residential SMB customers in a much more targeted and granular way. But the other part is now I have Ethernet to the node, and that Ethernet node not only is a DOCSIS element, it's also a Care Ethernet access platform. So you can provide cell tower backhaul services or Care Ethernet business services. So you get a lot of benefits there. And then obviously, one of the key things is we look at an architecture that provides a stepping stone to the evolution, right? So, we see fiber to the home is obviously a key part of any evolution for an MSO network. So this isn't about just saying DOCSIS is the only way to go. It's about providing a platform that is DOCSIS today and evolves to PON as MSOs evolve to that architecture. So you get to use the same fundamental network architecture, the same Ethernet node technology, the same 10 gig backhaul, aggregating into the same MX routing platforms, the same power of our software controller, independent of whether it's an Ethernet service, a PON service, or a DOCSIS service. So we kind of put that all together in that sort of unified virtualized CCAP architecture. And with that, I will hand it back to Jeff.
All right, thanks, Samir. I'm going to hand things back quickly to Andy to go over Juniper's product lineup. So, Andy, I'm cue things up for you.
Yep, so just real quick to review. We think that cable operators require modern networks, and at Juniper, we're investing in the building blocks to build these networks from the data center, where we have our new architecture called MetaFabric, which encompasses storage, compute, and SDN overlays in such a way that we can build very agile data center systems. We think that the cable networks of the future not only will be oriented around the metro, but will be very much oriented around a data center. We mentioned the core. We're building these lightweight transport-oriented routers in which we can integrate optics and then use software to optimize the path selection algorithms that are applied into these networks. And we think that this is a key to building scalable cable networks in the future. Everyone knows the MX, this notion of a universal edge or being able to aggregate multiple dynamic, different last-mile networks into this cable network. But today what you have typically in a cable network is this chassis CCAP, like Samir mentioned, and we propose just simply eliminating that over time and deploying these Ether nodes directly back into the MX chassis and separating the control and data planes for cable. Separating control and data planes is a fundamental base principle that Juniper believes in on how to build scalable networks, and the great thing about the virtual CCAP architecture is we follow that exact same playbook again. So like I mentioned in my talk, that the big goal here is to build an all-packet, end-to-end delivery system for all cable services, residential, commercial, and whatever new service might be built on top. If we can apply packet switching to the maximum degree possible, the network becomes simply a transport for any new application that may come along. So if you guys are interested in learning more about our building blocks for cable, our specific products, you can please reach out to your local Juniper account team. But between our PTX, which is our core router, the MX, which is our edge router, the virtual CCAP work that Juniper and Gainspeed are doing together, our QFX switching and software, Juniper has a very good story to tell for cable. The role of an edge router is to add value to packets. The role of a core router is to transport those packets very efficiently. And we can go into any level of detail that you might like to. So and with that, I'll pass it back to Jeff.
Okay, thanks a lot, Andy. Normally at this time, I'd spend a minute or two wrapping things up with conclusions, but what I'm going to do in the interest of time, since when I asked for questions, you all certainly more than generously responded. I want to save some more time for questions. I'll put my slide up here so you can just take a look at it, but I want to get right into the questions now. And the first one. So, Andy, this is one definitely for you. How do you see NFV, so network functions virtualization, management, and orchestration, bringing changes to cable infrastructure so cable operators can do things like dynamic service chaining and also change their revenue model for their services?
That's a great question. So when I said before that an edge router adds value to packets, NFV kind of follows that same notion, right? A packet comes in, it goes through certain appliances or service chains, and hopefully the packet that comes out is something that the operator that can then bill for, create revenue for. We've actually done quite a bit of work between Juniper and Gainspeed to see how can we integrate NFV service chains into DOCSIS provisioning. What we would like to do is to be able to define in the cable modem boot file either the service chain itself or be able to define a reference to a service chain so that when a modem comes up, and regardless of where that modem comes up, it can still receive the same NFV benefits and the same classifiers they use in DOCSIS today, the same class policy used in DOCSIS today, all gets linked directly to this notion of building a service chain. In fact, we presented this as a concept at NCTA in 2013 to gather a lot of really, really good feedback from the industry. I think myself that we see in the industry this notion of triple play or voice, video, and data not falling apart, but maybe not selling at the same rate it was before. So the new bundle of cable services may very well be NFV chained packet services, firewall, net nanny, cache, content filter, analytics, and so forth, that the cable companies can then craft a new product offering for subscribers.
Okay, great. Thanks, Andy. Next question, Samir, is for you, and this is certainly a good one. So you talked in your presentation about full spectrum, both you and Andy did full spectrum DOCSIS. But when is that going to happen? How do cable operators deal with, obviously, the troubling issue of legacy broadcast services, analog video, digital video, linear TV? How do they deal with that in this architecture?
Yeah, no, that's a great question. I mean, so when we talk about full spectrum DOCSIS, we're talking about the platform that can be used today in a full spectrum DOCSIS environment. So if you wanted to, you could take a 1 gigahertz plant and do 158 6 megahertz carriers as DOCSIS. But we obviously understand that operators aren't going to be able to move to that day one. So it's about providing a platform that they can then leverage the power of software to morph over time to get more DOCSIS as they need it. But in our architecture, we have the ability to carry all of the legacy services, whether it's analog video, whether it's digital broadcast QAM video, whether it's video on demand, switch digital video. So part of our sort of solution architecture enables all of the legacy services over that same Ethernet node platform. But as operators turn some of them off and free up spectrum, they can now turn that spectrum instantaneously into DOCSIS services and broadband revenue rather than waiting for a new hardware upgrade. So the whole notion of full spectrum DOCSIS and that full bandwidth is you want a platform that has that today and supports all your existing services, but then gives you the ability, as your business evolves, to start going through and transitioning spectrum to DOCSIS and to broadband services, which obviously are higher margin and higher ARPU.
Yeah, and I'll just add to that analog video and QAM video is to cable what TDM was to telco, 10 or 15 years ago, right? And TDM networks were in place. They made a lot of money. They worked well, but no one was investing in it. Same way how QAM video is in place now. It works well. It makes a lot of money, but no one's really investing in it. And the way that we evolved the telco space to a packet world was being able to tunnel TDM over packet, which is kind of where MPLS came from. So in cable, we think that we can repeat the same thing, that we'll take QAM and analog and tunnel it over IP, that's the best way to then gracefully enable a transition towards an all IP last mile.
All right, thanks guys. Thanks for the responses. Samir, I want to go back to you for one more question here. You mentioned in one of your slides that MDUs are kind of the logical initial step for this distributed CCAP architecture. Why can't, I mean, are you excluding the rest of the network, or is it just what makes that the right first step, and obviously when is it appropriate to start deploying it throughout the rest of the network?
So the technology is applicable to the entire cable HFC network. The reason we think MDUs are a logical first step is, a couple of things. One is you look at the demographics of who's living in a lot of these MDUs, apartment complexes in the Bay Area, Boston, New York. You've got a lot, it's a younger generation. It's more about internet broadband speeds, the millennials, right? So their consumption is different than, the kind of the different, older demographic, right? That's one part of it, so there's demand there. The second part is MDUs are actually a unique challenge because they're multi-year contracts, so you got to win that up front. The owners have a lot of say in terms of who gets that contract, and so there's this big pusher on gigabit and beyond. So you need that sort of next generation experience, and so our technology is a logical kind of baseline for you to use to build that, right? Because we can get you that gigabit services today and scale that in a very simple way. And the third piece is, MDUs are not a good fiber to the home play, right, as the alternative to gigabit, because a lot of them are older. You don't have conduits. You don't have structured wiring. Construction costs to pull fiber to every unit are pretty high. And then some MDU owners don't want you, drilling holes and pulling fiber. They want to leverage the infrastructure that's already there. And your choice is twisted pair or coax. And, coax has a lot more potential in terms of bandwidth capacity than twisted pair. So that's why we think MDUs are the first sort of logical choice, because it's just a very interesting problem that we're seeing in all of our conversations with MSOs today that's sort of top of mind. And our technology is very uniquely suited to help them address that. But we expect to use this technology in the entire network, right? For single family homes, any sort of deployment. Anywhere you put a fiber node today and have HFC access, you can leverage virtual CCAP. MDUs aren't the only use case. It's just sort of the top of mind use case for MSOs when we talk to them today. Got it. All right. Thanks, Samir.
So last question for Andy, and this has to do with M2M, machine-to-machine, and IoT, Internet of Things. How do you see cable networks evolving to support sensor devices like that, and then also employing more analytics, especially as they move into mobility services and more cloud-based services?
Yeah, that's a great question. I mean, you really can't talk about machine-to-machine or IoT without talking about IPv6. And V6 is critical to building a network that can support hundreds of millions of devices. My house has a dozen devices in it now, but that could quadruple easily in the next couple of years, and I don't think that's atypical. But the thing that's important about V6 is that if, as an industry, we agree that the killer app for V6 is the internet itself, and that this notion of unfettered packet internet connectivity between devices is valuable, then, which I do, and Juniper certainly does, then the thing that's most important about V6 is to keep it stable and predictable. It's very important that the spec for V6 be stable and be consistent, because we need to make sure that not only the big router vendors can implement a secure and scalable and reliable V6 stack, but that all of the factories around the world that are stamping out IoT devices can do the same. And that requires a lot of predictability and stability in the spec for V6. And second, we want to keep the V6 spec stable and predictable, because if you're a network operator out there, you don't want any uncertainty in V6 to potentially lead you down a path of choosing to deploy more NAT. which would work backwards from the goal of M2M or Internet of Things. NAT in the network works as a bottleneck in many, many ways. We could go on for that for another hour. But regardless, I think that IoT cable has done the exact right thing by deploying V6, by being V6 advocates, by pushing V6 out to the really as widely as they have. And now the key is to make sure that V6 remains stable and is implemented well across the ecosystem.
All right, thank you very much, Andy, and Samir as well. I'm going to hand things quickly over to Joanne just to wrap up with some more logistics.
Great, thanks, Jeff, and thanks to the audience for attending first, and of course, thanks to our panel, some really good information here. We really appreciate also the audience questions. So as we mentioned before, I know there were a lot of questions we didn't get to. The panel will follow up after the webinar. So thanks to Andy and Samir, to Juniper and Gainspeed for a great presentation. Thanks to Jeff Hainan also for leading that presentation. And just so the audience knows, the webcast will be available shortly on demand for the next 3 months. Here you can come back and visit the content again using the same link you used today, or you can share it with colleagues you think this might be of interest to. Also, we hope you join us for more Infonetics webinars in the future, so be on the lookout for those. We hope you enjoyed your time with us today, and then again, thank you for sharing your time. So have a great rest of the day, everyone. Bye-bye.